Hello everybody, welcome into this video. In the last video we finished off with an NACA0012 comparison of the NACC0009, which has become, through this playlist, what seemingly is our baseline airfoil, and what we've compared and which we will stand to compare will be measured up against. We did find with the NACA0012 airfoil and its shorter cord length that it still resulted in a higher drag coefficient and a higher drag force. Of course, it seemed to be counterintuitive in that we would have thought, on first consideration, I suppose, the fact that the airfoil with the lower surface area, i.e. the area that top and bottom, that would be given by the cord length, broadly speaking, by the span of the wing, multiplied by 2, obviously top and bottom. The one there with the smaller area would have less skin friction, and indeed it should, and if it has less skin friction it should have less drag, and yeah, that is true if that was all that drag was a function of. But indeed it's not just skin friction that drag is a function of. There's other anomalies that happen, especially in the flow regime that we're dealing with, which is transitional, Reynolds number of 50,000. In that flow regime, yes, there's going to be effects that are going to impact the drag and increase it, that are associated with that movement from a laminar flow regime into tubular flow regime. Now, all airfoils placed in a Reynolds number of 50,000 airflow will not have the same effects. So if you think about the onset of turbulent conditions, or the transitional effect, that will occur at different locations and at different sets of conditions for different airfoils. So every airfoil in 50,000 of a Reynolds number will not see the same onset of transitional conditions, and indeed any transitional conditions that are there will be at different kind of intensities, if you like, per airfoil. So the NACA0009 seems to be more resilient to the onset of transitional turbulence than the NACA0012. And we know the NA0012 at Reynolds numbers of 50,000 is particularly susceptible to transitional conditions, which is corroborated by numerous academic publications looking at that particular airfoil in these in this sort of Reynolds number flow regime. We're at an angle of attack of 0 degrees, so it's not as intense as if we did run with higher angles of attack. But nonetheless, even though it likely has a lower skin friction by virtue of the fact that it has less surface area for a given thickness, the NACA0012 is producing more drag because it sets turbulent conditions on much easier than the NACA0009, which remains more laminar. Definitely not 100% laminar, but definitely more laminar. So if you think about the if you want an analog, if you take a pot of boiling water and you know that water boils at 100 degrees, take that as an analog, that you know that a flow is going to turn fully turbulent at 500,000, say in flat plate theory or the likes of that. If you use the boiling point to Reynolds number of 500,000, you see hints, indications that something's going on before 100 degrees. If you look into the pot of water, now you see little bubbles forming there in the base of the pot, and maybe a bubble gets up and bursts on the surface, and if you put a thermometer in, you know you're not at 100 degrees. We just do not have that sort of average molecular kinetic energy that's given us 100 degrees in there. But very same in a Reynolds in a Reynolds number of 50,000. We're only a tenth of what's fully turbulent flat plate theory, but we are using Reynolds average navigator stroke, so we are looking kind of broadly as an analog to temperature. It's just an average of the amount of energy in that flow regime. And then if you look at the airfoil itself will be the ability of something to stop it boiling. So think about the airfoil as salt. Right. So if you for instance, the NACA0012 represents maybe a pot of water at coming until 100 degrees with no salt on it. It's going to boil at 100 degrees, and it's going to start boiling much easier at a lower temperature. Whereas the NACA0009 might have a whole punch of salt thrown into the water, and it's going to take higher temperatures, for it to phase change at that. So the NACA00, apologies for the analogy, maybe it's gone a wee bit out of hand, but the NACA0009 is less likely, apparently, to facilitate the onset of turbulent conditions, resulting in a more sustained laminar flow at them Reynolds numbers. With the NACA 0012 is showing signs of transition, whether it be bubbles forming at the surface, very small at 0 angles of attack, but nonetheless there is transitional effects there, and the NACA 0012 facilitates transitional effects much more. And that's probably why there's higher drag, even though there's less skin friction on it. However, what I'd like to do now is I'd like to stick another airfoil in here, one whose thickness to chord length ratio is greater than the 9% of the NACA 0009 and less than the ratio of the NACA 0012. And the reason for that is that I would just like to see if I can get a grip on what the skin friction effect is. So this airfoil that I put in should have less skin friction than the NACA 0009. It should have more skin friction than the NACA 0012 because at say 10 or 11% thickness to chord length ratio, I should have a longer chord length for a given thickness. I'm going to stay with 2.25 millimeters in this, like the earlier ones. But I'd still like to see what happens to the drag. Even though I'm going to have a lower skin friction than the NACA 0009, is that proportional to the increase in drag in the same way that the NACA 0009 and NACA 0012 have manifested? So what airfoil we're going to run with? Well, I'm going to run with an SD8020, which is a Selig-Donovan 8020. It's an absolutely phenomenal airfoil at these Reynolds numbers, and it performs extremely well at angles of attack of around 0, 1 and 2 degrees. So where have I come up with that one? Well, I've used that in a couple of other studies that I have done on external flows over airfoils at these sort of Reynolds numbers, and I first come across it in a document there that I normally always keep fairly close here to myself, which is the summary of low-speed airfoil data. It's a publication there by Michael Selig himself et al. That's a copy there of my ring-binded compilations of them. There's 5 volumes in this series of low-speed airfoil data, volume 1 to volume 5. If you're into, say, airfoil design for wind turbine applications, the later volumes are particularly interesting, particularly useful, specifically volume 5, I believe. However, in volume 1, chapter 1, there's a list of the airfoils that are tested. Well, that's the same with every volume. In chapter 1, the NACA 0009 is tested by Selig, but also the Selig-Donovan 8020 is tested. There's also another brilliant airfoil in there, the J5012. I believe it is, and the J5012 is a good alternative for the NACA 0012 at higher angles of attack. Just a wee bit of additional information there. It is not as susceptible to the onset of laminar separation bubbles at higher angles of attack, and where they do form, it is kind of more friendly, more favourable to the reattachment of them bubbles than the NACA 0012. What I found anyway. Now I haven't published anything on that, and I hadn't really intended to, but certainly if you are interested in something like that, let me know, and let's do an analysis together on it. Right, so yeah, maybe what I'll do, I have brought it up here as well in prep on this video, that the summary of low speed data, this is the document here, this is volume 1, the 5 volumes. There you can see the website that you could get it on. So this PDF, as well as the PDF of the other 5 volumes, are on mselig.ae.illinois.edu/UIUC. So the UIUC has an awful lot of absolutely phenomenal airfoil data, sections of airfoil data. If you scroll on down till chapter 1 on here, past all this, this should be it just here now, I'm thinking. List of symbols, and then we'll come on into chapter 1, hopefully. There we are, tested. Down here, these 4 are the symmetrical airfoils that are tested in volume 1, and of course you see the NACA0009 and the Selig-Donovan 8020, SD8020. That's the one we're going to look for. Okay, so to look for that, I'm going to go into Edge, because for some reason Airfoil Tools is just not working on Chrome for me. And let's take ourselves into Airfoil Tools. Lovely. So there's 2412, the default one. I am going to do a database search, text search, and SD8020, of course, search. Instead of done these here before. And there it is there. There's the 8020. And it's described there as a low Reynolds number airfoil. See, phenomenal. You can see here as well that its max thickness is 10.1% of the chord length, and that's located at 27.5% of the chord length downstream from the foremost point on the leading edge. What I want to do now is I'm going to send this here to the airfoil plotter. It's 100 chord length, that's not right. So I want to get a specific chord length to maintain a 2.25 millimeter thickness for an airfoil whose thickness is 10.1% of its chord length. So what I'm going to do is come back on in here into OneNote, and we've done this exact exercise here for the NACA0012 in the last video. I'm going to just put, just for the sake of consistency and all, I'm going to take a copy of that, paste that into there. That'll be right there. And what I'll do is come onto here onto the pen. Just wait for this to kick in. There we go. I'm going to take off the reference to the NACA0012. Right, and this 18.75 was specific for that, and because that was the NACA0012 was 12%, I take that away. So for a Selig-Donovan 8020 airfoil, the 2.25 millimeter thickness. Let's see, pen keeps flicking off. Right, the chord length will be, one back pen please. There we are. Apologies, the chord length is 10.1% of the thickness, so 2.25 divided by 0.101 is going to give me a specific length. This is Selig-Donovan 8020. So to calculate that, I'm going to scoot myself here into MATLAB, and I want 2.25 divided by 0.101, and I'm down to 22.2772 millimeter for a chord length. So I'm going to keep 4 significant digits on that, and I'll go for 22.2772. I'm going to go for 28. Right, which means that this length, the chord length, from the leading edge to the trailing edge is indeed 22.28 millimeters. This is given for a 2.25 thickness. Indeed, my thickness is going to be slightly more because I've rounded up my chord length there, albeit slightly. But nonetheless, 2.25 will be a very good estimate for it. And pull this over to the side. So 22.28 is what I'm looking for here on a chord length. 22.28. All right, let's get a plot for that. All right, and let's get the CSV files for this. So there's our CSV file. I'm going to open that on up, and what I'm going to do is I'm going to come back into here, into my airfoil data folder that I have. From these last videos, you'll see how I've created these. I did say in the last video that I'm going to reorganize these for a spreadsheet maybe, or a workbook per airfoil as opposed to a chord length. Chord length seemed like a good idea at the time. I'm going to copy that one and paste it. F2, and I'm going to call this airfoil plots. This is going to be for any airfoil that I have. Whoops, F2. Any airfoil that I have with a chord length of 22.28, and I'm not likely to have many of them. But dot. All right, let's keep that in there. So there it is in there. Let's open it on up. All right, I'm going to change my name here, rename this to Selig-Donovan 8020. Keep this in caps, SD8020. I'm going to take out these first 3 columns and I'll come back into the data that I had. Control C. I'm going to copy the first 3 and I'm going to paste them in there. I'm going to validate that my normalization here to the origin has happened. So 22.280 is 28.280, 00 to 00. So again, usually these symmetric airfoils are already normalized. But it's when you come to the non-symmetrical ones, like the 2412, 4412, and them sort of airfoils, this normalization procedure saves an awful lot of hassle. So there we go. That's what I'm going to do. That's auto saved. Take these 3 lines, Shift, Control, and down, Control C. I'm going to copy them. I'm going to take myself on into Notepad. I'm going to create a new Notepad and I'm going to paste them into there. File, and I'm going to save this as. I'm going to take this on into CFD, airfoil data. I'm going to put it obviously into the Selig ones, but I'm just going to come into these to take the naming convention just to keep consistency. I don't have a folder for this just yet, but now I do, an SD8020. Let's put in a new folder for 2D analysis. And let's change our file name to SD8020. This particular file has the coordinates for a 22.28 millimeter chord. That's that. Let's close that. Let's close that. No need to keep anything on that. Close that. Let's bring that down. Let's take ourselves back into ANSYS. What I'm going to do is I'm going to take a copy. Now I'm going to take a copy of the NACA0009 airfoil as opposed to this one. Geometry, mesh, and duplicate. Why? Well, it's easier to adjust the geometry of a thin airfoil to have it replaced with a thicker airfoil, as opposed to take a thicker airfoil and reduce the geometry down. That's the only reason I went for that one. This one here doesn't matter. I can take either of them, and just to show that, I'll just take this one. I don't want to keep the upstream stuff because I don't want it to reconnect back into this one. I do want this one to connect into here. I'm going to rename this one here. Need to rename the whole lot of it to an SD8020, and this one is a Fluent for the SD8020. Grand. Now I'm going to move into the geometry of this, and I'm going to replace what is the geometry of the NACA0009, this one up here in System A, with the SD8020 coordinates. And that's spline. Yeah, that took me a while to figure out that it's easier to go from a narrow airfoil to a thick airfoil than from a thick airfoil to a narrow airfoil. It's just how the domain gets split up, you see. So like there's a nice thin airfoil. What I'm going to do now is of the NACA0009, I'm going to go to Insert Geometry, and there's that one there. She's normalized. Now you see her here. There it is there. Absolutely phenomenal airfoil. Look how much shorter it is. Right? Like obviously that's 25 mil. That's 22.28. Right? Which is great. However, the profile is more or less the same. It does tail off here very quick, so maybe like the separation effects might be a little more prevalent, but again that's largely a function of angles of attack and Reynolds number, so only can find out how it's going to perform. Right. What I'm going to do is I'm going to fill up this region on the outside here. Right. So let's go for design, and I'm going to have to fill up the region here of this other airfoil in here. Oh. Make sure you select the boundaries. Yep, there we go. And that's it, tick. And there she is, right? So I'm going to take this one here, and I'm going to take that, and I'm going to project it. Click that onto this surface. Grand, lovely. And now what I'm going to do is take this out, delete that. It's gone. Now, you see what I mean? If I had a narrow airfoil, or I had a thick airfoil and went to the narrower, this line here would not have come down to hit the surface, and I'd have these two areas connected, and I'd have to split them. Now, it's not the end of the world, but it's a wee bit quicker. Now, because it's symmetric airfoil as well, I know when I split this, I should come straight onto the tip of this airfoil. If I don't come onto the tip of the airfoil, it's going to have problems with my map mesh, because my map mesh is dependent on me clicking onto the very aft edge of this. So I'm going to click this one here. I'm going to go for split. Right. Let me see if I can take the control point. See here, like, you're not, maybe just about. See it there, it's not just hitting onto the very aft in this, it's not coming into a solid point on this airfoil. That could cause trouble. So I'm going to undo that, and what I'm going to try to do is I'm going to try to split it from this side here, from that, which I know this is symmetric airfoil. I should be going right onto the last tip of it there if I hit that point. Let's see, it's probably going to be the very same. No, it isn't. See, that now has worked in phenomenally well. If I had a heavy airfoil and I went down to into a thinner one, I would not have been able to do that just as well. So if you at all can, I'm going to try to keep the try to go from a thin to a thicker airfoil. Right? Now I still need to split this. Now this here could still cause trouble. Split, but hopefully it'll just see it has done the exact same thing as I was worried about. So even though I've clicked that dot, it's brought it in around here. So it's going to be maybe a little bit less likely that I'll be able to get a structured mesh in there. What I'd need to do is update the geometry on this one here, maybe to bring that into a point in a much better fashion. Why did it happen on this one and not the other ones? Well, the other ones I always selected closed leading edge. I didn't have the option on this one because I didn't find this one by the NACA 4-digit generator. So seeing like the 4-digit generator, you have a option to close the leading edge, and this will come until a point, whereas in the earlier one here, we don't have that option to close the leading edge. But we'll see how it goes with the mesh. Anyhow, okay, so what I'll do now is I'm going to make a repair here, and I'm going to merge that and that tick, and I'm going to merge that and that tick. That's it. 1, 2, 3, 4, 5, 6. 6 faces. The lines do not look particularly straight. That might be that I'm just a wee bit off. Yeah, that's it there. It's a wee bit better. Okay, let's delete out our curves. Don't want that anymore. Right, because I want my edge. I'm going to now go on in and check my name selections, check my inlet. Inlet looks good, outlet looks good, and I've lost my wall. So I'm going to select my, going into design here, I'm going to select my edges of my wall if I can. And 1, 2, no, not that. 1, 2, 3, 4 edges. Come all the way around, open that up, and let's go for a wall. Okay, again, you know it's a wall by that symbol, you know, which looks like a kind of an opened up diamond, if you like. That's why I always delete out the curve and the sketch plane. If you delete the curve, there's a risk there that you're going to select the curve as opposed to the edges when you hit a name selection. And you'll know you've done that if you see X's and O's and some sort of geometric shapes instead of this symbol. All right, so delete out the curve. You don't need it at that stage, or you can right click it and just remove it from the physics. So there it is there. All right, there's our file. All right, let's go on into mesh, read the upstream data. And this is going to be the teller. If again this doesn't come in as structured as I want aft, I'm going to go on ahead and I'm going to run it anyway, and just so we can keep this video moving. How would I fix it? Well, I'd go back into the geometry maybe, and I'll tell you actually what you could do is if you go online and you go to big file. It's a great website. So if ANSYS Discovery isn't bringing in the geometry the way you want it, if you go into big file and you do a search for an airfoil, let's go for an SD8020. Right, there it is there, Selig-Donovan. If you click onto this, there you have your DAT and your DXL files. So I click the DXL file. There's a DXL file of points and a spline of points. Bring it down there, certainly. Take in the DXL file, go into AutoCAD and make your own spline around it. Right? And then you can be 100% sure that you've picked up the aftmost point on the trailing edge. Alright, so that's what I would do. So let me see, I'll just download that anyway. And there it is there. Right, so you'll open that up in AutoCAD and do it. So if you want to see me do that, let me know in the comments, and there's no problem doing it. But we're at 26, 27 minutes now already, so I want to just keep this moving. But that's how I would do it. All right, so I'm just going to exit on out of this. I'm going to click onto the mesh. And of course, we're going to have problems with the mesh. Edge size in here, I should have 7 edges. I only have 3. Which ones do I have? I have obviously that front one. And it's probably the 2 out here. Well, there's one there, 2, and I have another one there somewhere. I don't know where it is. But what I'm going to do is I'm going to select all the ones I want on the edge. No, that's I have 1, 2, 3, 4, 5, 6, and 7. There's 6 edges. 1, 2, 3, 4, 5, 6, 7. Not name selection, geometry selection, apply. 7 edges, long last. Now bias factors. That's good, that's good, that's good, and that's good. 1, 2, and 3 are back to front. 1, 2, 3. Bias factor that, but reverse bias of them 3. Job done. Let's go on to the next one here. This is edge size. Well, let me just rename this so I know. Rename. This is edge size in gen underscore ff, general flow field. This one here is edge size and rename hyphen aft. So 3 edges were all good. Everything looks good. Bias looks good. This one here has no selection, so I don't know what it was intended to be, but this one most definitely must be the inlet. Has 2 edges. I should have 4. 1, 2, 3, and 4. Apply 4 edges. There's no bias. That's it. Edge size in F2 hyphen inlet. So the last one by elimination must be the wall. So I'm just going to F2 that one here. Edge size in 3, wall. In fact, I don't know why I kept the integers in there. Edge size, gen size, F2. in that. Let's fix up the wall. No selection at the minute, but I certainly want 1. I want 2. 3. And 4. Play. No bias, everything good. That's it. So for each one of these, I want to make sure that blend to neighbors is set to no, 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 no. Mesh facing. Now I have 2 faces given to this. I'm on smart select here, so I can just click away. 1, 2, 3, 4, 5, and 6, and play. 6 faces. All right. So this now is going to be our test, to see how the aft edge of this had dealt with this new split. Either we're going to see a full map mesh after this, or we're not. So let's go on ahead here and let's generate that new mesh. That worked out all right, worked lovely. That's okay. So what you might have had if you didn't get that split just right is that you might have had your triangles aft again, but we managed to split it just okay. That was able to pick up the mapping based off the edge sizing, so that worked out very nice for us. So again, common stands as per the last videos, there is an awful lot of places here where we'll be able to make this mesh slightly better, but again, that's for an occasion where we have more time to do it. Okay, so let's close down out of this one. And I'm going to save up the workbench just at this. This is kind of, like, call it a milestone event when the mesh has come out in a way that you could recognize it as being favorable. Alright, so what I also want to do is I want to update my project now, because I want to send this mesh down into the setup. This setup is the setup here from the NACA0009, not from this mesh. Just because I've updated the mesh here does not mean that I'm going to automatically shoot my information over into setup. In mesh, I could have went up and I could have went to update project as well in there, and it would have sent my data across. Now I'm going to go into setup here. I'm going to open up the Fluent solver. I would like to be able just to go into parameter set and hit calculate the new design point. I would be able to do that, other than the fact that I am using a named expression in here which is looking for the cell zone, the flow field cell zone name, and the flow field cell zone name that I now have is going to be something like flow field -2. This would be flow field, this would have been flow field -1 as it was a copy. This would be flow field -2, which is a copy, but the name selection that is coded in that is still looking for flow field, which will just be flow field now because it was flow field 1 because it was copied from this one. All right. So of course this is all going to give errors just at the minute. I should have actually updated it in mesh. It would have saved a lot of this hassle, but we knew that was going to happen. I'm going to go into setup. And maybe it's just as well we've done it this way because we'll be able to see this in the console. Now what the error was, let's move over this control. Up, up, up. All right. All right, starting up nicely. General materials. Right. Parent mesh for display, setting mesh expression. So here you are. Here's the problem. Error. Right. Name cell count is not defined. Why? Because what it's looking for in here is a thing called area-disk_flow field. And obviously you cannot find that. We do not have that. But what we do have, we can see, is if we go into File and we look at recorded mesh operations, and what we can do is print incoming zone names, I could see in here that I have a thing called solid-sys-2_flow field. Right? I have this in here. Right? I'll maybe just try this here. I'm going to take a Control-C of that. going to close it. I'm going to be able to see it here anyway, right? But this is something that we do not have in our named expression. And the named expression, as we can see from up here, is looking in the cell count parameter that we made. There's cell count invalid, it says. So let's manage these here. Let's look at cell count and edit it and see what it's looking for. So it's looking for solid sys -1 underscore flow field. Well, there's no such thing. But what we do have is solid -sys -2 underscore flow field. So what I'm going to do is I'm going to just click into that. Cursor never appears in this whenever there's an error, but if you clicked after the 1, no, the cursor's there. Backspace, take it out, put in a 2. Let's refresh value, and there we are. Current value 165,600. It's up. Not worrying about the parameters again. Leave everything as it is, and let's close her up. That's it. Job done. Right, so we have to, because it's a copy and paste job, that's the price of speed, is a little bit of corrections along the way. Let's run into initialization. Let's initialize this off the same initialization that we ran with in the last time. So I haven't changed the amount of iterations or where I'm iterating from. Indeed, it is hybrid. What I'll do now is run into the calculations, not change anything at all. Run it out. Whenever this stops ticking round, let's give it a second there to execute. Alright, gotcha. Let's go to run calculation and let's just simply calculate. So I'm going to run this. When this solution is complete, we're going to go back into the parameter table, and we're going to very enthusiastically consider the value for the drag coefficient and the drag force. And see how it compares to both the NACA0009 and the NACA0012. So there we are, away we go. I'm going to press pause, and I'll come back on into ourselves here now whenever the calculation's been complete. Okay, everybody, back again. The calculation is complete, as you can see, and it did take the whole of 681, but our residuals are down to a phenomenally low level, and I think it could have been the lift coefficient that took a little bit of time, which we should expect would have took a bit of time, and indeed it's probably something that we could have taken off a convergence criteria, convergence condition, but nonetheless it is done. I'm going to quit the application here, and we're going to revert back into our table of design points, and let's look at the values for the drag, both force and drag coefficient, and see how the three airfoils compare. Let's give this a little bit of time to cool down and shut down. Don't want to rush it. Workbench. See all ticks, always looks good. But I'm not going to run out too much. Here we go now. Okay, let's hit a save on that. Irregular, and there we go. Let's see, 1738. They were earlier warnings. Okay, let's look at it now. Right, let's separate it. There's our parameter set, and let's see what we have. Now, of course, we can look at them here. Maybe try it this time. So the output parameters, these are my meshes. I'm not going to worry so much about these, the NACAs, but here we are. So there's the drag coefficient. So the NA0009, let's look at the coefficient. So I'm at a 0.159 for this one. In fact, what I'm going to do is just keep a solid record of them here. I'm going to 1. There is the 1, 2, and our most recent, the 8020. Let's take ourselves on into OneNote where we will be able to Windows V. Let's put the first down, which was the NAC0012. Let's put our second down, which was there's the 009. I actually should have had first. There's the 9. We move the 0012 over as our second in comparison. There's our first one, and V. Let's get our SD. Okay, let's rank these. So, of course, Anyway, let's go for this. Is the drag coefficient here in the middle, 0.0159442, 0.0166558, so this is still the best, and 0.0157. Look at that. Selig-Donovan is actually a better airfoil with respect to drag than the NACA0009. Let's look, so this is ranking in number 1. Drag force is giving me 0.202 newtons, where this is giving me 0.205 newtons and 0.215. So coming into this analysis, my airfoil of choice for this front wing application, probably the rear wing application as well, would have been the NACA0009, because I only compared against the 0012 and it outperformed it with respect to drag. Now putting in the Selig-Donovan 8020, I see there that outperforms the NACA0009 at this Reynolds number, at that angle of attack. Why? What's the difference? Well, it's just as I hoped that it might be, is that the Selig-Donovan at 10.1% of chord length given a thickness has a smaller surface area than the NACA0009. So this one here is 22 point, we'll put it in at 2728 millimeters of a chord length, where this one here was at 25 millimeters of chord length. So for a given span, say of 25 mil, this has a smaller surface area, so it should have less of a skin friction. So should this one. However, this airfoil here, obviously with respect to turbulent effects and the what's going on in the regions where it's transitioning from laminar to turbulent flow, it performs better. Again, without further analysis and just completely reading into this from a purely number and results perspective as opposed to an analysis-based confirmation. It has a greater surface area than the NACA0012, as the NACA0009 also has a greater surface area. However, it's still down on drag force with respect to the 0009. So it's not. This hasn't outperformed the NACA0012 of skin friction likely, but the SD8020 probably its lower skin friction has probably brought its drag force down below the NACA0009, and that coupled with the effect, the transitional effects, which are better managed by the SD8020 compared to the NACA0012, has resulted net in a lower drag coefficient and drag force. So this is now my airfoil to run with for me, Selig-Donovan 8020 with a 10.1% of chord length, giving me a thickness 1, 2 and 3. Okay, so I think it's getting back to the drawing board. Anywhere that I had an NACA0009 airfoil, I think it's time to move it over to Selig-Donovan or an SD8020, and maybe see can you recover a 100th, maybe, if not 1,000th, of your 20 meter drag, or hopefully lack of drag race down the track. So yeah, test another airfoil for yourselves. Pick it up off Airfoil data, off Airfoil tools. Have a look at the Selig publications on low speed airfoil data. See one there that you might think might be beneficial. Have a read through the academic publications, read through anything that Selig has published themselves. Read forums as well with respect to what people put up for, say, model aircraft, wind turbine blades as well, low Reynolds number regimes, and see what they find work well, and bring that airfoil in and test it. All right, but at the minute, yeah, Selig-Donovan 8020 looks very good to me. Finish off, what we probably should do, and what you should always do in these anyway, is always check your contours just to make sure that nothing is way off, which I wouldn't think that it is, but we should definitely bring them in and compare them to the other ones. But let's just see what we can see here. Alright, so we're going to be checking the graphics. The other thing there, what I just didn't look at straight away, just when I'm here, I'll do it now, is our Y plus values. Let's go all the way down here. I'll just check it here. There it is, max Y plus 0.08. So yeah, the 4 equation SST model is still fine with that Y plus value. Graphics, contours, see the first contour I have was pressure. Alright. That's very nice looking. Very indicative of the NACA0009. 09, yeah, got them all right there. Velocity, velocity magnitude, special. So we looked at all these were when we put in the angles of attack. Zero angle of attack, I don't think I put in a zero angle of attack comparison. But yeah, looks very well behaved now, and we're very well resolved. Zero angles of attack. You know, we could probably resolve it a wee bit up here, a wee bit more, if we did want to capture an effects of laminar separation. But certainly from, if we did want to look for laminar separation bubbles on a zero angle of attack, we probably most definitely need to go, need to go to a transient analysis as opposed to the steady state analysis. But yeah, let's keep moving. So next video, it'll be a while now before I can get back onto these. I know it's been these have been a long time coming, but sometimes it's just difficult to get the time to sit down and do these uninterrupted. But the next one, what I certainly want to do is I want to stick the wheel of the car in behind the airfoil to see what's happening to the air off of the airfoil itself, and look at the drag on that. And we might just do that, might just double it up and do that in 3D as well, and that'll kill two birds with one stone. In that we'll look at the wheel and we'll also have moved into 3D, and then we'll keep that same 3D one looked at in steady state, and then we'll do a transient version of it, which is going to be computationally expensive, heavy, but hopefully it'll some new physics, some new points of consideration might just pop out of it and help us make a more informed decision on how we're going to get the car down the track as fast as possible. Okay, so yeah, thanks again for watching the video. I hope you enjoyed it. I hope you'll be able to take something from it. I hope you'll be able to use it, and I hope you'll be able to find inspiration to keep developing your car up to regionals, through regionals into nationals, and then all going well into an international competition, which, by the way, I have heard is back in Singapore this year in October. So yeah, that's hopefully you find that as a nice wee piece of motivation. So again, thanks very much for your time. Let me know what you think in the comments. Any points, any suggestions, any questions, put them to me, please. And yeah, if you want to see some more of it, yeah, just hit subscribe. People have been telling me that I should be telling you to do this. So yeah, at least then I'll know that there's a little bit of interest in what's being done here, and it'll keep my own motivation going for it as well. Okay, everybody, thanks very much.